homework finished. Is that already going? Oops. Not even sure how I did that. Okay. So, yeah, we'll finish up preliminaries, answer any homework questions, and then move on to section 1.1. You don't have to have your homework ready for me for the preliminaries today, so we'll get that next time. Now, if we finish 1.1, we'll get 1.1's homework next time as well. I think we'll get back on schedule today. So all we have to get through today is 1.1 and the rest of preliminaries, which I think we'll do to be back on schedule.
How are we not on schedule?
We were supposed to finish the preliminaries last time, but I didn't really expect us to, which is why I only did 1.1 for week 2. So it's almost going as expected. Okay, so quick recap from last time. We started out with the field axioms. And if I mention something here that you have any questions about, let's rehash it out really quick. So field axioms, we'll just cruise through it all. Addition's commutative, addition's associative. There's an additive identity element. There's an additive inverse element. Multiplication is commutative. Multiplication is associative. There is a multiplicative identity element. For every x, there's a multiplicative inverse element, as long as that x wasn't 0. This is how we distribute, and finally, 1's not equal to 0. Any questions with the axioms?
Okay. We didn't prove a couple, though.
These weren't proved. These were our axioms. And then all these theorems are things that we proved. So I listed out everything that we proved last time. So first thing we proved was there was one and only one 0 element. Well, we already knew that there was a 0 element from our axiom. Then we proved that there's only one 0 element, so there's a unique one. Our next proof was that any number times 0 is 0. Then we proved that if the product of two numbers is 0, then one of the numbers was 0. Good? Then we proved that for every x, there's one and only one additive inverse element, right? And so we defined negative x to be the y that makes x plus y equal to 0. So since there is one and only one y that makes x plus y be 0, then we can now define that thing. So we call that one and only one y that makes x plus y 0, we call that y negative x. That was our definition of negative x, right? And then we came up with the definition for subtraction. X minus y is the same thing as x plus negative y. That was just a definition, right? Moving on, we proved that negative x is just x. We proved that negative x is also the same thing as negative 1 times x. We proved that negative x times y is negative x times y. We proved that x times y is negative x times negative y. We proved that that negative 1 times negative 1 is 1. This was just a corollary of this. When you plug in 1 for x and y, then that turns into 1 times 1, which is just 1. This one we didn't do, so I'm going to crank this one out real quick. Theorem 10. So we're proving that x times y minus z is equal to x times y minus x times z. And I noticed in our lecture we didn't do this one, so let's do it real quick. So we have x, y, and z in the real numbers. That's what we start with. So x times y minus z. Now what is y minus z? Using our definition, y minus z is y plus negative z. So y minus z is y plus negative z. Now we know how to distribute a multiplication across a sum. That's the distributive axiom right here. And so that enables us to go from here to here. Now we know that negative z, where is it? Right here. Negative z is the same thing as negative 1 times z. So going from here to here, all I'm doing is replacing the negative z with negative 1 times z. You good with this? Am I just leaving you behind? Or are you right there with me?
Yes.
All right. And then we know that multiplication is commutative and associative, so I can move the negative 1 out front, grouping those together, and rewrite it like that. And then negative something is the same thing as minus that thing. So I have a plus negative 1 times b is the same thing as a minus b. And we're done. Any questions on that proof? All right. Moving on, another one that we didn't do. Proving that negative x minus y is the same thing as negative x plus y. So starting out, let x, y, no z, let x and y be real numbers, then negative x minus y is the same thing as, we can turn that negative into a negative 1 on both the numbers. So I'm turning this negative into a negative 1 and this negative into a negative 1. I kind of cheated there, huh? I need to take this from here to here and then replace it with the negative 1. So I did 2 steps in one going from here to here, but you good with it?
It's not a big leap.
Yeah, not a big leap, which is why I accidentally did it. Okay, and then I can distribute this negative 1 across this sum. We distribute this negative 1 across this sum, so we get negative 1 times that and negative 1 times that. Good? And then we have our axiom, or our theorem, that negative 1 times negative 1 is 1. So going from here to here, we replace those 2 negative 1s with just a 1. And I know that negative 1 times x is negative x, and I know that 1 times y is y. And we're done. Any questions on that one? Okay, back to theorems that we proved last time. We proved that not only does every x that's not 0 have a multiplicative inverse, but there's one and only one multiplicative inverse. So for every x, if x isn't 0, then there is one and only one y that I can multiply x by to get 1. Good? So we proved that one last time. It was very similar to proving that 0 is unique as well. And then, now we can define that, and we forgot to explicitly write down this definition last time, I think. So, whatever that one and only one y is, that I can multiply x by to get 1, I'm going to call that y x to the negative 1. Now it's important at this point that we do not know that x to the negative 1 is some operation that changes a number. We're not viewing that as an operation. This is a way of marking a number. The same way that we didn't view negative as an operation, it's just a way of marking a particular number. Make sense?
Until we define it as an operation, right?
Right, we haven't defined to the power of. We don't have that. Notice we don't even have a bunch of numbers, like we don't even know what 2 is yet. We have no definition for 2. Notice every time we're dealing with things, they were already referenced here in the axioms. Or we proved them explicitly. So I didn't rely on some backhand knowledge that I know that 1 times 1 is 1, and going from this to this. I used a proof that I had for that. So just keep in mind exactly what this gives us. We're not saying x to the power of negative 1 is equal to y. We're saying x inverse is y. It's a labeling. Anyways, so now x inverse, what does that symbol mean? That means the one and only one number that when you multiply by x, you get 1. Good? So then we prove that the inverse of the inverse just gives you back your x. And then we proved the inverse of negative x is the same thing as a negative of the inverse of x. And then the last thing that we proved was the inverse of the product is the product of the inverses. And that catches us up with everything we did last time. Good? Okay. So, moving forward, the next natural thing to do now that we have this multiplicative inverse defined is to define addition very similar to the way that we defined subtraction. The same way that we defined subtraction was x plus the additive inverse of y. We're going to define x divided by y as x times the multiplicative inverse of y. Our only restriction here is y can't be 0. So, for all x and y, where y is not 0, we define x divided by y to be x times y inverse. Now, why can't y be 0?
Because it's undefined. And
Well,
x divided by y is undefined later.
That's the high way of saying it, but from our axioms, we only knew that when x wasn't 0, we had an inverse. We don't have a multiplicative, we're not guaranteed a multiplicative inverse if y is 0. We're only guaranteed a multiplicative inverse if y isn't 0. That's what we proved. We proved if y is not 0, then it has a multiplicative inverse. So you might be tempted, as you're doing proofs down the line, to multiply both sides of your equations by the multiplicative inverse of a number. You need to be careful to make sure that that number is not 0 before you do that. It's something that's going to come up in proofs, and I think we'll even get one today.
Why aren't we also saying x doesn't equal 0 for that?
X can be 0, perfectly fine.
I know that, like as an operation, 0 divided by something is a number.
X is always just a number. I'm not guaranteed that y inverse is a number. The only way that I'm guaranteed that y inverse is a number is if y is not 0. This symbol, y inverse, is only defined when y isn't 0.
Oh.
That's the only time we have a definition for what that is.
Right, right.
Over here I have x inverse. Don't be confused by the switch between x's and y's.
That's what got me.
Okay. So the way that I'm using x's here, I'm using y's here.
Right.
Good? Okay. So now let's do a quick proof using this definition of division. What are we going to prove? We're going to prove x plus y divided by z is the same thing as x divided by z plus y divided by z. Pretty straightforward? Okay? So let x minus z be real numbers such that z is not 0. Notice that this is only defined if z is not 0. Because whatever's in the denominator is a multiplicative inverse of something. Whatever's in the denominator is a multiplicative inverse of something. I can only have a multiplicative inverse if it's not 0. So let x, y, and z be numbers such that z is not 0. Then x plus y divided by z, using this definition, is x plus y times z inverse. Use the distributive property, go back to our definition. Straightforward, nice and easy. Nothing weird there. Okay, so that is the end of our proofs using the filled axioms. Now we're moving to our next set of axioms. So throughout this class there's going to be 3 sets of axioms that we're using. The filled axioms, the positivity axioms, and then the completeness axiom. So we're done with the filled axioms, now we're going to move to the positivity axioms. The positivity axioms are what gives us order in our set now. So they should give us a way of saying this number comes before this number, after this number, something to that effect. So what do the positive axioms say? The positive axioms say that there is some subset of the real numbers that we're going to call positive that satisfy these 2 things. Okay? So 1, if x and y are positive, then so are x plus y and x times y.